Welcome to Project 10. In September, Orange Labs proposed to us a new way of interacting with the urban environment. A city-wide sensor network, measuring data of all sorts in real time, openly accessible to the world for use in any application one could imagine. Our job for the past few months has been to develop ways in which this could be done. The requirements come in two sections: requirements for the system infrastructure and requirements for how the system would operate in a particular use case scenario. First, the system infrastructure. The system must be built around a central server. Data from the sensors placed in situ throughout the city will send their data to it wirelessly. This system must be open and flexible, and allow for new sensors to be easily added to the system, as well as taking data from other open data sources. Finally, this system should be set up in a way that allows for an API to be produced, in order for developers to make use of the data as they please. The use case scenario that Orange Labs have asked us to investigate looks at cars and street-side parking bays. The system in this context will be using street-side sensors to monitor the state of parking sensors across the city, whether or not they're occupied by a vehicle. The main requirement of this system is the accurate detection of a vehicle's presence in a bay. The data will be read and fed to a central server using the general system infrastructure. The hardware detectors must be designed so as to be cost-effective, resistant to the elements, functional in most environmental circumstances, and maintain a long battery life. Through extensive research, we developed conceptual designs for this system. Initially, we had to look at how to send the data from the sensor to the central system. An option was to simply use a Wi-Fi module to make a connection with each individual sensor. However, this could have resulted in hundreds of Wi-Fi signals, all within a few tens of meters, being connected to the same address, a highly inefficient use of power and money. It would also have meant the modules would require larger batteries, and consequently larger casings, making discrete integration with existing architecture a challenge. From this, we moved on to consider the idea of grouping sensors by zone and having them feed their data wirelessly to a local node on the system. This node would then connect it to the database using Wi-Fi and upload the data from each sensor in its range. The two most reasonable options we researched were to use Bluetooth or Zigbee. Bluetooth has the benefit of a larger range than Zigbee, and with the new Bluetooth 4, there is no limitation on the number of devices that can be paired. However, Bluetooth is more power hungry than Zigbee, and may be the inferior choice where sensors are within a short range, or nodes are numerous enough that full coverage is achieved. A final option is to connect the sensors to a node directly with a serial cable, which will be more secure, but comes at a data rate distance exchange. Laying all the necessary cable would also present many issues, and would render a plug-and-play architecture impossible. The decision was made to prototype with Bluetooth. Next, we considered ways in which the system could be implemented in terms of vehicle detectors. Through our research, we decided upon a few primary methods of detection: infrared distance finders, electromagnetic field detectors, and piezotronic force sensors, amongst others. The context in which the detectors will be deployed involves many conditions which all need to be satisfied, at least to some degree, in order for the system to be reliable. These include the system reliably reading the presence of a vehicle in the bay, the system continuing to operate in adverse weather conditions such as fallen leaf coverage, to be protected from vandalism, to consume as little power as necessary in order to maximize working life, and to be easy to maintain, along with obscure edge cases such as detecting when a car is only overlapping a bay and not fully occupying it, for instance if it were hauling a trailer. With infrared sensors, there are many methods of implementing a detector module, and each has mixed results. Placing a sensor in the middle of the ground pointing up can result in interference from the sun, and wouldn't reliably function if it dirtied or half the bay was occupied. A more reliable solution would be to lay a track of infrared sensors spaced at regular intervals and angled at 45 degrees along the base of the curb. These would detect an obstruction more reliably, but it would be very susceptible to dirt and waste vegetation buildup. Piezotronic force sensors implemented in a flexible membrane would provide the best results performance-wise. A wide-spaced grid of these sensors could accurately read a car's points of contact with the road, based on where the force distribution is. The system would work regardless of vegetation or dirt buildup, and could even offer richer data, such as detecting how many people are in the car, or analysing whether an available space is wide enough for a particular model. However, this system would be unreasonably expensive, and potentially difficult to maintain. We will carry out further tests for each of our system designs in Term 2. For the purposes of developing a prototype, we have decided to use an ultrasound sensor. The system design comprises 4 distinct elements. First, the node sensor pair in the environment. Sensors in the road communicate via Bluetooth to their associated node, or zone controller. Then, the zone controller sends that data via Wi-Fi to update a row or multiple rows in the database. This data can then be interpreted and analysed by a virtual machine, with the processed data being provided in the new table. Finally, through the Web API, developers will be able to access this data for use in their various applications. To prototype this as a demonstration of proof of concept, we modelled a subset of the system that's structured in exactly the same way. The roadside sensor was modelled using Arduino Mega, wired up with an ultrasound distance finder, and a Bluetooth transceiver. The code running through the Arduino waited for a request from its parent zone controller, modelled with a laptop, before taking the average of 100 readings and sending the result. This ensures that no battery power is wasted by constantly reading a stream of unused data, and also greatly improves the reliability of the result. The laptop simulating the zone controller ran the main Java software code, consisting of 4 classes. In a real-world implementation of the system, each zone controller would run this code. The main function loops indefinitely, making a request to the paired sensor every 60 seconds. A connection is made using the RxTX.com library in Java, and the data is transmitted through serial ports. Once the data is obtained by the laptop, it sends an update query to an SQL database, before beginning the loop again. The SQL database used for this project is hosted on Windows Azure. This simplified the process somewhat, as Microsoft offered a Java library specifically for Azure SQL connections. The database had to be carefully designed, with multiple considerations in mind. It's important that sufficient information is available for anyone wishing to use the database, whether it be developers, researchers, or maintenance administrators. A sensor metatable holds metadata describing each sensor. Most fields in each row would be set when the sensor is first added, such as the unique sensor ID, but the status field is updated on every sensor read. If for whatever reason the sensor returns a predictable false value, for instance a negative value in the case of an ultrasound distance finder, the status will be updated to false. Our sensors row in the table was created with the unique identification number of 1 for both the sensor ID and the node ID. The field measures describes what the sensor is being applied for. In our use case, this is parking. Other examples may be pollution, heat, or wind. The type describes the sensor, the model stores a specific serial number, and the position data at the end is used for spatial processing and applications involving geographical analysis. The raw data that the Java code updates is stored in sensor raw. The field reading float receives the updated result, and each update is given an associated timestamp for analysis purposes. The table nodes stores data about each node, or zone controller, and again only the status field is updated. This is set to false if the node experiences an interruption during the 60-second sleep period. Finally, the table holders is another metadata table, used for storing information about those who own and operate a sensor on the network. This will be more rigorously used in Term 2, when we experiment with ways for external users to add their sensors to the network. With this data all now in place, analytics can be performed. Using a Java API, again running on a laptop, the data is read from the tables using SQL queries and processed. The output is then fed into a new readings table, parking, specifically designed for processing data from parking sensors. The analyzed data is what the web-based API will access primarily, in order to save developers from carrying out the basic operations on the raw data themselves. In the context of parking sensors, for example, it would be far more useful for us to provide a true or false parking spaces occupied field than the centimeter value from a distance finder. The system can now be demonstrated. This Java code is already running. The current reading in the sensor raw table is 37 centimeters. I'm going to put my hand in front of the sensor and see which updated result we get. At this point, the Java code is looping whilst it waits for the connection to the serial port that the Arduino is running on. The connection is made and the status LED on the ultrasonic glows while the readings are taken. This data is then returned to the Java code, where it is concatenated into an update string. A connection is made to the SQL database, the query is submitted, and now the new value appears on our sensor's row, 6 centimeters. With the work that we've carried out this term, we've demonstrated that our system design is realistic for satisfying the requirements. Our initial plans to code the software in Java, using Bluetooth to transmit between sensors and nodes, have proven successful. There's a lot of expansion, development, and experimentation to be done before the system can be fully satisfactory. For example, our prototype highlighted layers of complexity that we hadn't seen beforehand, specifically the demands of building scalability into the infrastructure, and designing an automated process for adding a sensor to the network. So, in Term 2, we plan to continue experimentation with an expanded system. Within this, there are 3 main areas of focus. First, testing of the hardware implementations for detecting a car parked in a bay. This is critical, as it will inform the configuration of the system for demonstration of the proof of concept. Second, expansion of the system such that nodes can successfully communicate with multiple sensors. Using RxTX communication through serial ports proves slightly troublesome when a node may only have one serial port to read through, and our current code doesn't account for this. We must also consider how new sensors might be added to the network, bearing in mind our client's request for a focus on plug-and-play architecture. As such, the final area for focus is the development of a comprehensive set of developer tools, including a Java API for handling software code, a web API for high-level implementation in things like mobile apps, and a web-based GUI cataloging every node in the system. These tools should include a simplified process to allow external persons to add sensors they own to the network, maintain them, and if necessary remove them. This kind of external interaction is critical for growing networks like this, and the more open and flexible the platform can be, the more potential there is for this to become a groundbreaking project.